Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1967 marks a pivotal moment in the history of astrophysics, a moment illuminated by the groundbreaking work of Jocelyn, Bell Burnell and Antony Hewish, encapsulated in their paper observation of a rapidly pulsating radio source. This discovery, initially met with both excitement and puzzlement, revolutionized our understanding of stellar remnants and the exotic physics governing them. To appreciate the profound implications of this observation, it is essential to trace its genesis, meticulously examine the work itself, and understand its lasting impact. The intellectual landscape preceding this discovery was ripe with advancements in radio astronomy. The post-World War II era witnessed the burgeoning of this field, driven by technological innovations such as the development of more sensitive radio telescopes. Previously, radio astronomy had primarily focused on the detection of continuous radio waves emanating from celestial objects. The discovery of the first quasar, 3C273, in 1963, a radio source with an incredibly high redshift, challenged existing cosmological models and opened up new avenues of inquiry. This work, by Martin Schmidt, demonstrated the unexpected breadth of objects emitting radio waves, which in turn spurred the design and construction of more capable telescopes to observe these phenomena. The Cambridge group, led by Hewish, embraced this new frontier. They embarked on a project designed to investigate the scintillation of radio sources caused by the solar wind, using a dedicated radio telescope built specifically for this purpose. The project's primary objective was to study the interplanetary medium by observing the twinkling of radio sources, akin to the twinkling of stars in the night sky caused by atmospheric turbulence. This research demanded meticulous data collection and analysis, and it was within this project that the crucial discovery began to unfold. The work itself, as detailed in the seminal 1967 paper, centered around the detection of regular, intensely pulsed radio signals. Bell Burnell, then a graduate student, was responsible for analyzing the vast amounts of data generated by the telescope. While scanning through the chart recordings, she identified a recurring signal, a scruff of radio noise, which appeared as a series of regular pulses with a period of approximately 1.33 seconds. This was a signal that seemed to originate from a single point in the sky. Initially, the characteristics of the signal, its brevity and highly regular nature, confounded the scientists. The prevailing understanding of astrophysical objects at the time did provide a working hypothesis. The team investigated a number of possible causes, considering and discarding options from terrestrial interference to more esoteric possibilities before settling on the idea of an astronomical origin. The discovery of this pulsating radio source, dubbed LGM-1, or Little Green Men by some, prompted a thorough investigation. The signals were found to have an extremely precise and regular period, a characteristic that distinguished them from known sources of radio emission. The team painstakingly determined the signal's celestial coordinates, eliminating the possibility of terrestrial or solar interference. The observed periodicity, the extremely short duration of each pulse, and the signal's high degree of regularity were all features that were extremely unusual for any known astronomical object. After further investigation, the team identified 3 additional pulsars, adding certainty to their findings. Their work culminated in the publication of the landmark paper, which presented the observations, analysed their property, proposed a framework for understanding the nature of these celestial. The immediate impact of this discovery was considerable, though it initially met with a degree of skepticism. The notion of a celestial object emitting radio waves in precisely timed pulses challenged conventional astrophysical models. The proposed underlying mechanism, a rapidly rotating neutron star, was a theoretical construct, and its observational confirmation was groundbreaking. However, the paper's publication ushered in a new era of astrophysical exploration. The identification of pulsars, objects with incredibly high densities and extreme gravitational fields, opened a window into the realm of relativistic physics. They provided a testbed for theories of general relativity and served as a unique laboratory for studying the behavior of matter under conditions impossible to replicate on Earth. The discovery galvanized the astronomy community, with other groups quickly moving to search for and study these newly identified objects. New observatories sprang up, dedicated to further refine the measurements of pulsar characteristics such as their periods, pulsation profiles, and spectral properties. This led to the immediate detection of a rapidly expanding class of new pulsars. These observations helped to solidify their understanding. It further allowed for study of their evolution and provided vital insights into the processes within the core of collapsed stars. The discovery also had a direct impact on numerous fields of physics, including nuclear physics, plasma physics, and even cosmology. The legacy of the pulsar discovery extends far beyond the initial identification of these objects. The study of pulsars has dramatically reshaped our understanding of stellar evolution. The observed pulsation periods provide a precise clock. They allow astronomers to test models of stellar structure with unprecedented accuracy. The detection of gravitational waves from binary pulsars, for example, provided the first indirect evidence for the existence of gravitational waves. This work, conducted by Joseph Houghton Taylor Jr. and Russell Allen Hulse, earned them the Nobel Prize in Physics in 1993. The discovery of millisecond pulsars, which rotate hundreds of times per second, provided clues to the long-term evolution of neutron stars in binary systems. The observations of pulsars in the centers of supernova remnants, the expanding clouds of gas and dust left over from stellar explosions, have led to a deeper understanding of the supernova process itself. Scientists have used pulsars to map the distribution of interstellar matter, to probe the behavior of matter under extreme conditions, and to test the fundamental laws of physics. They have explored the environments of black holes, and have even been studied in efforts to detect evidence of gravitational waves and to explore the universe's most energetic event. The original work by Bell Burnell and Hewish, while groundbreaking, also faced its share of critiques and revisions. While the initial data analysis and interpretation were meticulously scrutinized, there were later refinements. For example, early models of pulsar emission mechanisms have been refined to accommodate the various observed pulsar properties, and the initial models describing neutron star structure have undergone continuous improvement. These critiques, however, were instrumental in refining the understanding of pulsars and their relation to the wider cosmos. The initial observations, while providing an important breakthrough, led to a series of deeper investigations. They also prompted the development of increasingly sophisticated theoretical models. The original identification of pulsars generated the interest of a generation of researchers. These scientists focused on observing and modeling the behavior of these fascinating objects. The initial interpretations of the nature of pulsars, while fundamentally correct, was soon augmented by the development of increasingly sophisticated theoretical models. The influence on subsequent generations of astronomers and physicists is clear. The discovery spurred an enormous wave of research activity. Numerous research groups around the world sought to observe and study these enigmatic objects. This led to the publication of thousands of research papers and the development of new observational techniques and theoretical models. The discovery has had a clear influence on numerous subsequent researchers. Bell Burnell's contribution to the field, while initially overshadowed, has been increasingly recognized. Her persistent identification and rigorous analysis of the initial signal were crucial to the ultimate discovery. This led her to become a role model for aspiring scientists. The initial work by Hewish, as the principal investigator of the project, was recognized with a Nobel Prize. However, the contribution of Bell Burnell has steadily gained greater recognition over time. The discovery of pulsars by Bell Burnell and Hewish represents a pivotal moment in the history of astrophysics. It demonstrated the efficacy of dedicated instrumentation. It underscored the importance of careful data analysis. It opened a new window into the universe, revealing previously unknown forms of matter and energy. The pulsar discovery serves as a testament to the power of observation, the human mind, and the relentless pursuit of knowledge. This work directly influenced subsequent discoveries in fields of cosmology, high-energy physics, and gravitational wave astronomy. Their work has solidified its place as a cornerstone of modern astrophysics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.